Hey guys, I'm reporting to you from generic rainforest here, where I've been trying to track down a very elusive and very rare boa constrictor, which has a highly advanced form of camouflage known as green screening. Haven't quite found it yet. We're here for another lecture today, and what we're going to be talking about are straight line solutions. Okay, so we're going to be dealing with, again, linear systems, and specifically for linear systems, those are really the only ones in general that you can discuss straight line solutions for. So to build this all up, I want to talk about the different pieces and the whatnot that come together to make this happen. A lot of it has connections to linear algebra, but hopefully I'll be able to fill in any gaps we have here. So in R2, I want to think about vectors as objects. Really, in Rn, that's fine, but we're going to just stick to the plane. Okay? So we've got some objects which are vectors, and we know them as just like, I'm going to do one, I think, in yellow right here. Wow, that is imperceptible. I'm not going to use yellow anymore except for highlighted. Okay, so I've got some vector v right there, which is a yellow vector. Bear with me, okay? Now, if I multiply that by some number lambda, what lambda is going to do is either stretch or squish it, all right? We collectively call both of these things scaling, all right? So lambda v is specifically scaling an object, okay? And so it can either make it shorter than it was before, it can make it longer than it was before. Heck, if it's negative, it can make it point in the opposite direction. But what's important here, if we look there, that's going to make a line, right? We can see how that's a line. Now, if we think about a matrix multiplied by a vector, okay, that's going to create a new vector. And so I have an object, I'm doing something to that object and creating a completely distinct other object in my space, right? That is not just shrinking or squishing it, okay? We're going to think of these matrices, matrix multiplication, as transformations, okay? That really go from evolving one object into another object, okay? And we want to keep this in mind and in line with where does A times a vector come from? It's the right-hand side of my differential equation. So A times a vector, that transformation of A is, in fact, what the dynamics are that are occurring. And a straight line solution would be looking for when A times some vector is equivalent to lambda times some vector. Or when I'm doing a transformation in a particular direction V, that transformation is the exact same as scaling in that direction. Okay? This is a very kind of, to me, it's a very high level question. Okay? I want to transform something, and I want to know in what directions is that transformation the exact same thing as just stretching or squishing. Okay? Now, if I look at that equation right there, the only thing that we actually know is A. We know the coefficient matrix. We don't know what direction and by how much the scaling actually occurs to solve this. So we've got several unknowns, because if I rewrite this problem, right, I've got my ABCD, that matrix, times the vector, let's call it V1, V2 for the elements of V, equals some lambda times V1, V2. Okay? Now, that's, first off, it's well posed. We get a vector equals a vector. They're the same size and shape. But we've got like three different unknowns, V1, V2, and lambda in there. We only have two equations. So we should already know that there's going to be some redundancy built into the solution here. We're going to find it, okay? Rewriting that as a system of equations and then just doing a tiny bit of algebra to that, we get that A minus lambda times V1 plus BV2 should equal 0. And similarly, C times V1 plus D minus lambda V2, that should also equal 0, okay? So we've got our system of equations that we have to solve. And what's nice is I can rewrite this again in matrix vector form just to kind of make a couple things clearer to us, okay? If I take a peek at that right there, we've got this matrix A minus lambda, B, C, D minus lambda, and the vector V1, V2, okay? Now, if we recall from April 6th's lecture, right, where we talked about, hey, when do these systems of equations have non-trivial solutions or not? The only time this has a non-trivial solution is when, well, it's if and only if the determinant of that matrix, A minus lambda, B, C, D minus lambda, if that happens to equal 0. Now, why would we want a non-trivial solution? Because remember, when we were looking at equilibria, we liked when we only have a trivial equilibrium. When we have non-trivial ones, we have a whole line. Well, the trivial solution would be the vector v1, v2 is the 0 vector. That's not helpful. There's no information in there. All this is saying is that if you start out with nothing and you transform it, that's the exact same thing as multiplying that nothing by any number. And that's not a useful thing. What we want to do is say, hey, I want to transform a vector, an actual vector I can see, not the 0 vector. And I want it that when I do my transformation in one of these directions, it's the same thing as just stretching or shrinking. Okay, so we want to find where the determinant of that matrix equals 0. And so we're left for solving this polynomial right here. Now look at that. The only unknown is lambda. Cool. Let's multiply everything out here. We get lambda squared minus a plus d lambda plus ad minus bc should equal 0. Okay. This is often called the characteristic polynomial of that matrix. The fact that that is the exact same terminology that we used before, not a coincidence. And in fact, we're going to have a short after this video where I just kind of explicitly show, hey, these polynomials are all the same, okay? You might be able to notice it here. That's great. So we can solve that for lambda. We get this big old ugly thing. And I think because I'm lazy and I just don't want to rewrite this over and over and over and over and over again, we're going to define a couple quantities. Let's let tau equal a plus d, and this is known as the trace of the matrix A. And we're going to let capital delta equal ad minus bc, which we should already know is the determinant of the matrix A. So this just lets me rewrite the solutions to lambda a little bit better, as lambda equals trace plus or minus the square root of trace squared minus 4 delta, all that over 2. Wonderful. So what we've just found now is that, hey, if we find that special direction, my transformation is the same as scaling by this amount. And what should be fascinating to us is that we have 2 solutions. Right, we get a plus or minus. So all of this should sound incredibly similar to things we've done before, because in some sense, it's the exact same dance to a different song. Okay? What I want to know now is, hey, how do I find that direction, that vector v, where my transformation is the exact same as those special scaling? Well, let's recall that lambda is going to equal trace plus or minus the square root of trace squared minus 4 times the determinant all over 2. Okay? And for now, I'm not even going to get into how to analyze these things. These are whole other lectures for next week. Let's just suppose that there's 2 real solutions, okay? So we're going to let trace squared minus 4 delta be greater than 0, just because that's going to help us out a little bit right now, so I don't have to handle a bunch of like special cases or whatnot. I actually don't even think I really need to make that assumption per se, but as long as they're real, that's what's important, okay? So ABCD times V1, V2 equals lambda plus, we'll just go ahead and grab that one, V1, V2, and now what we know is we know ABCD and lambda plus. So now we have 2 equations, 2 unknowns, but they're the same equations we started with. We had 2 equations and 3 unknowns. We got rid of one of those unknowns. So now what we should be identifying here is that we have an underdetermined system, meaning that I've got 2 unknowns and really only one more fact to play with. And so we should have redundancy built in. Let's look at it. I take the very first equation from that, and I'm going to solve it for V1. It's going to equal B divided by lambda plus minus A times V2. Let's do the same to the second equation, okay? And we're going to get, my mustache itches, lambda plus minus D divided by CV2 equals V1. Now, if V1 equals this, and that equals V1, then this should equal that. All right, so let's do that. Let's say, okay, so B divided by lambda plus minus A, V2, is supposed to be equal to lambda plus minus D over C, V2. Move this term over to the left-hand side, and we'll do a little bit of factoring. Okay, this means V2, there we go, multiplied by the quantity, and it's a big quantity, lambda plus minus D times lambda plus minus A minus BC, all that divided by lambda plus minus A times C. This should be equivalent to 0. Okay, that's just algebra, just moving my phone apparently still works in the rainforest. It's good to know. Okay. Now, that numerator there, that lambda plus minus d times lambda plus minus a minus bc, that's the exact same as what we already know is supposed to be equal to 0. So I know everything in those parentheses is equal to 0. Now, this entire equation should equal 0. And if that equals 0, then v2 can be any damn number we please. It could be 10. It could be negative 5/8. It could be pi over 6. It could be... Sure, let's make it equal 1, right? That's the easiest number to work with that actually has information in it. If I made it 0, it wouldn't tell us anything. Okay? So if that equals 1, well, then what am I left with? Well, I know v1 is equivalent to b over lambda plus minus a. In fact, you can use either of those expressions for v1, and you'll get the exact same number. And so we've got the direction, where v1 is the first element of the vector, and the number 1 is the second element of the direction of the vector. And like I said, we'll work more on this, but that's essentially how you can find eigenvectors. To me, that's the easiest way. Sometimes they'll be an ugly form, and then you can just do multiples on them. So we'll talk more about eigenvectors and eigenvalues, which are those amounts, the lambdas, and the directions. And then we'll interpret those things in terms of what it means about solution stasis. Okay? I thought I felt something on my shoulder. I still gotta look for that snake. How do you attract snakes? With food? Alright, bye-bye.